All right, in this video, I'm going to cover section 2.5, Accelerating Convergence. So in this section, the goal is to learn Atkinson's the delta square method. So that's the algorithm to accelerate the rate of convergence of the sequence, which is the linearly convergent. Okay, so regardless of its origin. So the Atkinson's so first we're gonna definitely we're gonna learn the Atkinson's delta square method, and then we're gonna combine the fixed point iteration method with Atkinson delta square method the to accelerate the rate of convergence of fixed point iteration method, because the fixed point iteration method is the rate of convergence is linear convergence, right? So we're gonna accelerate, I mean, improve the convergence rate of the fixed point iteration method by combining it with the Atkinson delta square method. Okay, so so here, let's see. First one, we're gonna consider the sequence Pn, which is linearly convergent to P. Okay, so here we assume that the sign of Pn minus P and Pn minus Pn P sub n plus 1 minus P and P sub n plus minus 2 P sub n plus 2 minus P, they have the same sign, which means that their signs are positive or negative. Okay, so then we assume that n is sufficiently large. At when n is sufficiently large, then those fractions are approximately equal. Okay, so now from here we're gonna derive the formula, Atkinson delta square formula. Okay, so then we're gonna the first one we're gonna isolate Pn plus 1 minus P. Okay, but there is a Pn plus or minus 1 minus P right there, so we're gonna multiply Pn sub plus 1 minus P on both sides, and then we're gonna multiply P sub n minus P on both sides, so we're gonna get this. And then now we do FOIL left hand side because there's square right there, so with FOIL, then we're gonna left hand side, right hand side. Okay, so then we see the p square, both sides, then p square will be canceled out in both sides, right? And then we're gonna the put all terms having p in the left hand side. Okay, so excuse me. Now then the p sub n plus 2 plus p, where these come from here. So we're gonna move this one. See that you see the pink box is move this one to the left hand side, and then we're gonna move p sub n plus 1 squared to the right hand side. Okay, and then these two pink box terms in the pink box have the p, right, common factor p, so factoring out p, so we're gonna get this, and the right hand side we're gonna get this. Now then solve the that one for p, that expression for p, we're gonna get this. Okay, so let me see. Oh, this I think give me a second, this is typo. Okay, so now okay, yeah, give me a second. All right, so now then we're gonna add and subtract the terms p and p sub n squared and the 2 times p sub n plus 1. Okay, so in the numerators. Okay, and the grouping terms appropriately. So what does that mean? So we see that here in the once we get this one, so far we got that expression, right? In the numerator, we're gonna add and subtract p sub n squared and the 2 times p sub n times p sub n plus 1, like this. Minus 2 times p sub n times p sub n plus 1, and then say plus 2 times p sub n plus 1, and then plus p n squared and then minus p n squared. Okay, so then the see that here, first three terms have common factor p n, right? And then okay, so we're gonna factor out p sub n in the first three terms. Okay, now then this one, do you see that the parenthesis, the blue, blue box, this is exactly the same as the numerator in the bottom, right? See, so we can separate this the fractions in these fractions, we're going to separate the what? This one. Okay. See, then we're going to get p. That's going to be equal to what? P sub n, right? Okay. And then the right hand side is a negative. The rest of the term in top divided by the denominators. Okay. So now we're gonna the what first one here in the sequence obtained by Atkinson delta square method is obtained by calculating this one. Okay, let's see that. So we can say we call that one. I mean the result of this right hand side to p sub n hat. Okay, so what does that mean? So here, then to find out, to find out the what to compute the sequence obtained by Atkinson's delta square method, first we need to find out sequence using other algorithm. Okay, so and then give me a second. Before going further, we need to figure out what the delta, that symbol, meaning of that symbol. Okay, so now I'm going to introduce the four difference operators. See delta, we see delta, this one. The name of this, we read this one as delta, and then in here that delta is called the four difference operator. Okay, defined by p sub n plus someone minus pn. Okay, so delta pn means that the next term in the sequence minus the current the term in the sequence. Okay, so now high powers of delta are defined recursively by this. Delta to the kth power pn is delta times delta to the k minus 1 power pn. Okay, then we can figure out delta square pn. That means delta of delta pn. But delta pn is what? P sub n plus 1 minus pn, right? So delta of p sub n plus minus p1, we apply delta into each term, p sub n plus 1 and p sub n. Then we're going to get delta p sub n plus 1 minus delta pn. Now, what delta p sub n plus 1 is what? P sub n plus 2 minus p sub n plus 1. And the delta pn is what? Pn plus 1 minus pn. Then, well, combining this and simplifying this expression, we get this. Okay, that's the what? Exactly same as what? Denominator right here in the Atkinson delta square method right here. And the top one is what? Just delta pn square, right? So we could express the Atkinson formula as like this using the delta, four difference operators. You will see delta four difference operator later. Okay, so just keep in mind this. So now the p and hat, the sequence obtained by Atkinson method, converts to p more rapidly than does. I'm not saying that this is, the order of convergence of Atkinson method is quadratic, but it's just more rapid than does original sequence. But we have not said what it means meant by the terms. How fast? Okay, so more rapidly. So how faster than the linear convergence? We'll see. So this is here, theorem 2.13. Okay, suppose that Pn. Okay, this just kind of regular, the sequence, okay, having the rate of with the order rate of convergence is linear. Okay, which means that r pi is 1. Okay, so converge linearly to p, then p hat converges superlinearly to p. It means that limit of p. What that means? What does that mean? Superlinearly to p. Okay, it means the limit of p n hat minus p over p n minus p is key. Look at this. In the numerator is p n hat, and the denominator is p n equals 0. In what circumstance that fraction equals 0? As n approach infinity, so that Pn approach P and Pn hat approach P. In order to that this fraction approaches 0, while Pn approach 0 and the Pn hat both sequence approach P, the numerator must approach P much faster than denominator approaching P. Okay, so it means that the numerator approaches 0 much faster than Pn minus P approach 0. Okay, so that's the meaning of that limit. Okay, Now I told you we're gonna combine the fixed point iteration method with the Atkinson delta square method in order to accelerate the order of convergence to quadratic. Now see, since the then Atkinson delta square method gonna boost up the order of convergence of fixed point iteration method up to quadratic, which means R pi is 2. Okay, so the method is called the Steffensen method. Okay, so here's the you know, the steps of the Steffensen method, okay, algorithm. So first one, P00 is the initial approximation, and TOL is tolerance, and the N sub N naught is a maximum number of iterations. And then P sub K up to, you see that, the superscript of parenthesis I, so I indicate the index of iterations, okay, and the K equals 0, 1, and 2. Now, see, first step is to compute the P1, P sub 1, and then, P sub 1, okay, in the still 0th iteration, okay? So using the fixed point iteration, P1 and P2, okay? So now, and then the next step, we compute the P01. That's the, see, that's the P0 hat, okay? Why? Because look at this formula. In the Atkinson, method formula, to calculate P and head, we need to, well, we need to know P n, n plus 1, n plus 2. We need 3 information, right? So that's why we had to compute P1, P2, in the 0 when I equals 0, okay, using the fixed point iterations, and then we calculate the P0 head, okay, using Atkinson delta square method. Now then, next iteration, okay, next iteration, we're gonna, actually that's the, in the step from the step 3, that's gonna be first iteration, right? So P1, the first iteration, we calculate P1 using fixed point iteration, but here, instead of using P what 20, we're gonna use the P0 hat, which is the first term in the sequence obtained by Atkinson's delta square method. Okay, let's see. And then we calculate P2 using P11. Okay, now and then we calculate the P1 hat. Okay, it's a P1 hat. So we're gonna repeat this. So here the main idea of the Steffensen method algorithm, we're gonna use the term, the sequence, term in the sequence obtained by Atkinson delta square method to calculate the P1 and P1, okay, to calculate P1 using fixed point iteration method for each iteration. That's the main algorithm. So here's a pseudo code. So you can see that here, P1, P2, we calculate P1 and P2 using fixed point iterations. And then here, P represent P hat, okay? Actually, P0 hat, right? Okay. So now in the back to here. So now you see that you can see that sub index never goes beyond the 2, right? Always, you see the subscript is always repeating 0, 1, 2. And then you see that a number in the superscript inside the parenthesis since that number indicate the index of iteration, so that one goes 1, 2, 3, 4, up to n naught. Okay. So what? So we're gonna, excuse me. So then p minus p naught. Okay. So if p minus p naught is less than tolerance, then p must be what? The we output p. Okay. So what if p is less than 10 to negative 16? Then it means p equals 0. Then output p2. Okay. Why? What happened? If p is SW of p is less than 10 to negative 16 means that p is almost 0. Okay. If p is almost 0, what happened? Then we're gonna get the excuse me. When you get 0, when you calculate the P1, now you see that eventually what? We P, which is a P0 hat, will becomes a P0. Okay? Understand that? You see that P0 hat becomes what? We're gonna calculate P1 in next iteration using P0 hat in a previous iteration. So that's the P0 hat. Okay. So in the next iteration, we're gonna calculate P1 using P0 hat. Is that P0 becomes P is what? Will be updated by P0 hat, this one. If a P0 hat is what, 0, then P1 gonna be 0, P2 gonna be 0. Next iteration, P1 gonna be 0, P2 gonna be 0, so we're gonna get the 0 in the denominator. That's a big problem, right? So we're gonna output just P2. That's the P2 is what? Actually, this one. Okay, since we cannot calculate, the P0 hat if the denominator is 0. Okay, we're gonna get the denominator 0. We cannot figure out the P. So we stop the implementing Atkinson method, and then we just return the P2. Okay, so that's the Atkinson delta square method. It's quite simple. Okay, so it's like a bisection method. It's quite simple, but since the two algorithms combined, you need to fully understand the Atkinson the method and the fixed point iteration method, and then definitely you need to implement the algorithm, okay, to solve some examples and then the homework problems. Okay, so let me stop here, and the next time I'm going to cover chapter 3.